Hello, this is the Mr. Maths channel. Today we're going to be going over the sums of series, which is a very large topic within further algebra and functions. It involves a bunch of different techniques that you need to use, such as evaluating definite sums, a lot of algebraic manipulation for simplification, and also a little bit of limits that we're going to learn. There's a very simple question, and what it is more formally referred to as is the Gaussian summation. I'd like to ask that question to you guys. I'll say that there exists a sequence which is 1, 2, 3, 4, 5, 6, all the way up to 100. And I would like to ask you, how would you add all of these numbers together? So what would be the sum of every number in the sequence from 1 to 100? And obviously just starting off doing 1 plus 2 plus 3 plus 4 plus 5 plus 6 and working through the problem that way, kind of brute forcing it, is clearly not the method, because first of all, it's very easy to make an arithmetic error, and second of all, it's just a very cumbersome way of doing it. There's a much faster, more elegant ways, and Gauss was, or instead Gauss is one of the first mathematicians who kind of worked out what the sum of this series could be. So the nice trick about this question is that we can consider two things essentially. 1, 2, 3, 4, and I'm just going to cut off the numbers. And instead of writing just 100 here, I'm going to write 97, 98, 99, and 100. Okay, so the thing you can focus on over here is that if you add 1 to 100, you'll get 101. If you add 2 to 99, you'll get 101. If you add 3 to 98, you'll also get 101. In the same way, you can pair every single number in the sequence up to another number over 50 that will equal to a sum of 101. Clearly, if you were to pair these up, you will get something of the sort like 1 plus 100. I've just bracketed it so that you can kind of visualize what I'm trying to do here. 2 plus 99 plus 3 plus 98, and all the way up to 51 plus 50, let's say. And all of this adds up to 101. So we get this much simpler sequence of numbers, which is just one constant added together however many times. And now we have to figure out however many times this is added. So let's kind of think about this. We've paired off the numbers, and initially we started off with 100 terms. So this is 1, 2, 3, 4, 97, 98, 99, 100 terms. Now I've thought about pairing the terms together. That means that I'll be left with half the number of terms because I've evaluated them. That means that I actually have 50 101s over here. If I multiply 50 by 101, that will be the sum of my series, 5050. And that is a much easier way to evaluate your sum from 1 to 100 than just doing, working through it like 1 plus 2 plus 3. It's just a hassle if you do it that way. And this can be extended to any linear sequence, obviously by using your first principles method, but it is very easy to prove. And if you have a sequence, because a sequence can be represented as a starting term, or at least an arithmetic sequence, it can be represented as a starting term A plus some common difference d multiplied by the nth term that I want to find. Then the sum, or actually I'll use a of n to represent the sum. A of n will then be a half n 2a plus n minus 1 d. It's really good practice if you want to prove this result, especially using the previous answer, kind of reach over and apply that sort of concept to any general sequence. And the way you'd go by this is that you'd start with your first term a, then you'd consider a plus d, a plus 2d, and kind of go on from there and start applying your principles. All in all, very satisfying answer that you can get out of this. And the nice thing is that this sequence is present in your formula booklet, so you don't need to worry about it. In a similar sort of way, you can evaluate the sum of the squares of all the integers and the sum of the cubes of all the integers, and thankfully with WJEC that's all you need to really work with. So another way I can represent the sum from 1 to, let's say, 100 is saying quite literally, or it's called big sigma notation, I have r equals 1 at the bottom here, which is telling me where I start from with my variable r, and then where I end. So let's say I end at 100. So this big sigma notation reads the sum of r equals 1 to 100. Or sum of r from r equals 1 to 100. And that, we worked it out, was 50 times 101 equals 5050. The good thing is that there is a general rule, and of course again it's an extension of the method that we applied. Instead of using just 100, we're using some general upper bound like n. So instead of using 100 over here, what we're going to do is we're going to use n. So if I just put an n there, and if you were to evaluate this, you'll get a half n plus 1. Yeah. So very nice, easy formula there. R squared is a little bit more difficult to evaluate from first principles. Besides, it's not even required by the WJEC spec for you to kind of work from first principles with, so don't fret if you can't prove these results. You're only required to apply them. This will be a sixth n plus 1 to n plus 1. Lastly, you're going to have the sum of r from r equals 1 to n of r cubed, which will be a quarter n squared n plus 1 all squared. And there's also another sort of sequence that is, I guess, pretty helpful to kind of consider. The sum from r equals 1 to n of 1. Or any constant, let's say a. You're kind of really asking the question, how many times do I add on a? And r is representative of that. Other than that, it's just a times n. So pretty simple work there. Where the questions with this differ is that they are very algebraically heavy. You need a lot of manipulation to work with these questions, and again, precision is very it's an integral part of this. If you aren't precise with your algebraic manipulation, then surely things could just go south and you won't get to the answer. But as things go, it is a further maths topic, so it you kind of need to expect that the demands of further maths are quite high, at least within your computational skills. So let's try and put those computational skills to the test. We are going to go through a practice question, and it's good to see, at least with some unfamiliar content or unfamiliar techniques, you can figure out a method for yourself and ultimately work through that. So I will pose to you a question. Find the expression for the sum from r equals 1 of r plus 2 all squared to 2m in the form a third m am squared plus bm plus c, where a, b, c are integers whose values are to be determined. So what we're trying to evaluate over here is r equals 1 to r, or of r plus 2 all squared to 2m. Very interesting variable choice over here, because we're using 2m instead of n. So it's a variable times a constant, or rather a parameter times a constant. So things will be a little bit interesting to work with that. Unfortunately, it's a little bit easier to work with less interesting things. So I think the first method, or the first step that you can apply over here, at least to, take your mind off things, is 2m equals n. So now you only have to worry about just one parameter instead of trying to work with 2m and maybe making a wrong substitution in your head. So this is what we're going to be working with. This expression right here cannot be evaluated very easily, at least in the form r plus 2 all squared. So the first thing to evaluating this sum is expanding this bracket, r squared plus 4r plus 4. The nice thing about sums is that they work almost like or they work in the same way as if you have your derivative or your integral. If you have the sum of two expressions of just the whole function, let's say r squared plus 4r plus 4, then you can distribute the sum between r squared, 4r, and 4. And it wouldn't change what the original operation was that we did to our function. So it's pretty flexible in that regard. Obviously it won't work with your multiplication because you are working with a sum over here. Ultimately, what you get out of this, if you were to break it up, and you can be a little bit lazy with the notation over here, because the r equals 1 and n are implied, at least in your methods, but I do recommend that you write them in so that it is it is really clear that what you're doing is coherent to the examiner. Another thing is you can move constants out of the sum. Okay, now that we've ended up from here to here, we can finally start applying the rules that I wrote down on the board from earlier, or the evaluations of r squared, r, and r cubed. Clearly r cubed isn't really necessary over here, it's not present in the expression, so we're going to use r squared, r, and the evaluation for 1. So the evaluation for r squared is a sixth n plus 1, 2n plus 1, plus 4, or of 4, and then the evaluation for r, which is going to be a half n plus 1, plus 4n. very long expression over here. So what is required of you in at least the exam is actually simplify this down into its, I guess, simplest state. So you have to kind of work with this in a way that is very easy for you to, evaluate the expression. And by that I mean not to expand the whole thing out, because obviously that is a very cumbersome method. It's not very resourceful as well, because you will be wasting a lot of time doing that. What you should do instead is you should factor out like terms between the different expressions added together. And clearly I can see that there's an n, which is a factor between all of them. And another thing is I want to factor out fractions as well. Working with fractions, it's really not nice within our algebra. Much nicer to work with integers, for example. So the main evaluation that you're going to be doing is within the square bracket, and very, very ideally they need to be integers. So any sort of fractions that you see over here, you kind of have to move them out of the expression, outside of the bracket, and then work with the expression. So if I move a sixth n out, because it is the smallest fraction, I'll get n plus 1, 2n plus 1 inside my bracket, plus, this was originally a 4 times a half, which is going to be 2. The only way I can get a 2, or the expression, the number that I have to multiply a sixth by to get 2, is going to be 12. So if I have a 12 over here and I multiply it by a sixth, I'll get 12 over 6, which will just simplify to 2. And that is what we need. So this will be a 12. The n is factored out, so it will be a 12n plus 1, plus, for a 4, I need, or at least if I factor out a sixth, what is left is 4 divided by a sixth, which will be 24. Clearly, at least the work now is a little bit easier than it was before, because you'll be expanding a cubic over here while working with fractions. Same thing over here, you'll be expanding a quadratic and then working with an integer 2, for example. So this is essentially just a smarter way of doing things, and will save you a good amount of time if you follow this method, as compared to, again, expanding the whole thing out, which is really not smart. Evaluating the expression inside the square bracket, what you get is 2n squared plus 3n plus 1 plus 12n plus 12 plus 24. If you take a sixth n out, or if you've kept the sixth n out, we can just collect like terms over here. So 2n squared remains as it is. 3n, 12n add up, so 15n. And then you have 12 plus 24, which is going to be 36. 36 plus 1, which is going to be 37. Some of you might be shouting, maybe, we've arrived at the answer. Yeah, but we also have the substitution that we did earlier, which is going to be n equals 2n. So no, we haven't arrived at the answer, because now the expression requires us to give our answer in terms of m instead of n, because what we started with was n. This is just a convenient substitution that we've made so that we don't make any silly errors, or reduce the chance of us making any silly errors. Therefore, what you have to do is you have to substitute back in. N equals 2m, therefore you'll get 2m over here instead of n, which becomes a third m, times by 2 times 4m squared, which will be 8m squared. This becomes plus 30m plus 37. Ultimately, this is the answer that you get. And that's how you work with this. The thing you have to really look out for is 2m, because now you have an upper bound that is it's kind of like an amalgamation of a constant and a parameter. The bad thing about that is that although you can apply your rules to this, so let's say a sixth n plus 1 to n plus 1, of course you can swap n for 2m, but it's very likely that you can make a mistake while doing that. So it's very it's quite resourceful if you want to equate something to something that's a little bit easier to work with, because again, if you have 2m at the start over here as well, then you'd have to do more arithmetic as well to work here. So here you'd have to factor a third m out instead, and the bracket will be whatever left inside. Overall, the method over here, if you don't equate 2m to n, just becomes a little bit harder and a little bit less nice to work with. So just look for things that you can, make a little bit easier at the start of the question, and then start the question. The second part requires us to evaluate, and the evaluation, pretty simple work. It's basically just substituting the upper bound into your formulae, if I haven't already said that before, but it should be pretty obvious. So this is our answer right here. We're gonna say evaluate the sum from 11 to 20 of this expression. I really should be using an r equals 11 over here, because for example, you could have multiple variables in your expression, and if you just substitute, or if you just write 11 at the bottom of this sum, then it isn't immediately clear as to what you should be evaluating. Same reason why you have a differential at the end of an integral, or something with respect to x, which you're going to be working with. Okay, this is a pretty interesting problem, because now we're working with a base that isn't 1. The interesting thing about that is that now we can't really use our formulas over here, because all of our formulas, if you didn't notice, they all start from 1. So they all take into consideration the sum from r equals 1 to n. This starts from 11. So as it is right now, this question, or this sum, we can't actually apply our formulas to it, because starting from 11, our formulas apply for sums that start from 1. So it kind of feels like we've hit a roadblock over here. But I'll make it easy to visualize by using the expanded out form instead of just using the big sigma notation. Let's, instead of having r plus 2 all squared over here, let's have like just r as an example. The sum from 11 to 20 will be 11 plus 12 plus 13 plus 14 plus all the way up to 19 plus 20. This is very similar to our sum, which we know the rule for, or the rule from r equals 1 to 20, and that will just be 1 plus 2 plus 3 plus 4, and then that just sums up, and then it joins our new sum, which is going to start from 11. 11 plus 12 plus 13 plus 14 plus all the way up to 19 plus 20. Clearly this sum and this sum are very similar, but this is the sum from 11 to 20 of r, and this is equal to the sum of r from 1 to 20. Clearly you can see that all the numbers up until and not including 11 they're missing from this expression right here. What you can conclude from that is that the sum from r equals 1 to 20 r will actually just equal this sum plus the extra numbers that you add in for your starting term from 1 to 20. So the missing numbers from 1 to 10, inclusive of 10. So from r equals 1 to 10 of r plus the sum of r equals 11 to 20 of r. So clearly you can kind of see a correlation over here. We can see that the sum from r equals 1 to 20 is just the sum of the first 10 terms plus the sum of the next 10 terms from 11 to 20, the same as 1 to 10. But now this is a very useful expression that we've kind of, deduced, because now this is just an equation. We can apply our rules. We can say the sum 20 r equals 11 over r actually just equals the sum of 20 r equals 1 of r minus the sum of r equals 1 to 10 of r. And the easier way to see that is the way to remove these terms is just by subtracting those terms. But so if I were to subtract these terms from both sides, I'll get minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7, minus 8, minus 9, minus 10. But that's just the sum from 1 to 10, subtracted. So if I bracket everything, this becomes a plus, 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 plus. There, you have the sum from 1 to 10 subtracted from the sum from 1 to 20. And that's where you get 11 to 20. So it's a pretty intuitive way of thinking about series, that they're quite literally just sums of numbers which are arranged in a certain way. But now we can use this sort of insight. We can answer our question, which was, what's the sum from r equals 11 to 20 of r plus 2 all squared? So what we applied over here, this applies to any series, because a series is quite literally just a sum of numbers, isn't it? So we can think about this in the same way. We can say, well, what's the sum from r equals 1 to 20 of r plus 2 all squared? Well, it's equal to our sum that we want to evaluate, r equals 11 to 20 of r plus 2 all squared, plus the missing terms, which is going to be r equals 1 to 10. Crucially, you don't want to go up to 11 over here, because this is r equals 1 to 10 inclusive. If you go up to 11 over here, then you can't start from 11 over here. And we want to start from 11. We want 11 to be part of our expression, so we can't subtract it off. So there you go. That's the expression that you get. If you subtract, so you can get this term to be isolated, it becomes r equals 1 to 20 of r plus 2 all squared minus the sum r equals 1 to 10 of r plus 2 all squared equals the sum of r plus 2 all squared of, well, starting from r equals 11 to 20. Now, it's just a matter of applying this expression that you worked out to this. And this is where you need to be a little bit careful, because this is an expression for 2m, and the top of the sigma, the top of the big sigma notation, 2m, will equal, let's say, 20, because that's our upper bound here. Therefore, the number that you're actually substituting in will be 10, because here you have the equality 2m equals 20, if you want to substitute n in, you have to use 10. If you have your original expression in terms of n, which, if I recall correctly, was this, then by all means, yes, go ahead, substitute 20 in. But if you're working with this expression, then you have to consider the kind of equality with 2n and the upper bound of our new sum that we need to evaluate. So what this expression becomes is a third m, which is going to be 10 for this, or if I'm going to look at this instead, because this is our kind of deduced expression that we need to work with. A third, 20 becomes 10 because we're halving due to our relationship, and then it's going to be 8 times 10 squared plus 30 times 10 plus 37, and then minus a third, because you're starting with 10 over here, we're going to use 5. It's going to be 8 times 5 squared plus 30 times 5 plus 37. Evaluating this, obviously you're allowed to use a calculator. So if you were to evaluate this, you will get 3,145. And that should be the final answer. The interesting bit with these questions is that oftentimes you kind of have to be very on your toes and figure out really what the expression is trying to tell you, because with this expression it does mean a very intuitive thing. It's quite literally telling you that I have this rule for which I get numbers out if I substitute integers from 1 to some number n, and I want to sum all of those numbers, and that is what this expression means. And we want to work with that, we want to kind of use that to our advantage and get to our final answer, which is what the question is asking you. Alright, so at least with the exclusive content, this is pretty much it for sums. Another a topic that you have to work with is the sum of infinite series, and it involves the idea of limits essentially. It's kind of asking really what happens to n as I increase n off to infinity, for example. So let's say I have some sequence n, or sorry, some series n, which I'll actually represent using r, because I'm starting off with r equals 1, ending at my upper bound n, of let's say ar n minus 1. This is a pretty standard series. This is a geometric series where you're multiplying by a common ratio every time. So if I were to expand this out, you get a plus ar plus ar squared plus ar cubed plus ar to the, sorry, I just defined it wrong. So let's use k instead. Ar to the k minus 1, so that goes up to n. So the final expression becomes a to the, or ar to the n minus 1. So that is your geometric series, because you're multiplying by a common ratio every time. What you have to consider is what happens when I take the limit as n goes to infinity of this expression. Basically, it's asking you, what if I keep adding more and more and more terms? So ar n minus 1 over here, or the n in this exponent, balloons off to infinity. And the first thing that may come to mind is this expression is gonna shoot off to infinity, because I'm multiplying by a number every time, and it's going to get bigger and bigger and bigger at a faster and faster rate, surely this sum is going to be infinity. That's true. This series could be a divergent series, i.e. if I keep adding more and more terms, the terms keep getting bigger and bigger and bigger at a faster and faster rate, ultimately ending up at least us having a conclusion that the series is divergent. It goes to infinity. But there's another question that you could ask. What if r was a decimal, for example? So if r was a decimal, instead of the terms getting bigger and bigger, they get smaller and smaller. So r, or ar, will be smaller than a. Ar squared will be even smaller. Ar cubed, likewise. All the way up to ar n minus 1. And clearly with that, you can kind of see that it does approach a value, maybe. But you don't know what that value is, do you? And the nice thing with geometric series is that there's actually a formula for you to work these out. The formula for just n is going to be a times 1 minus r to the n over 1 minus r for any r. If you take the limit of that as n goes to infinity, provided that the modulus of r is less than 1, and by that I mean r is between 1 and minus 1, then we have this expression. If we kind of look at it and apply our rule, we have n, which is going to be a very, very large number at some point, and r, which is going to be a decimal. Clearly that's going to approach 0 because we're multiplying a decimal by a decimal by a decimal all over again, and that decimal is less than 1. That means that we're going to get a smaller and smaller output every single time until ultimately you have r to the n, which will just be 0. 1 minus r stays unchanged over here, so does a, because it has nothing to do with n. It's a parameter of its own. And this is the expression that you get. So this is a pretty useful expression over here. Although very underused in the WJEC mathematics spec, it is within your formula booklet, and the good thing is you'll only really need to remember the theory behind all of this, and not even that much. Just be a little bit aware, just have it at the back of your head, because it's useful for answering questions. But this idea of applying limits can be used for basically any series. So if you have the sum of some fraction, okay, so if I have like 1 over r instead, and if I say r equals 1 to n, and I take the limit, n goes to infinity, then you can apply this idea to this sequence as well, and surely you can get a number out of it. I say that, but this series actually diverges, and there's a very interesting reason why. This series will just be the sum of the harmonic series, which is going to be 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5 plus 1 over 6 plus all the way up to 1 over n, and then you could just take the limit as 1 over n goes to, or both of these expressions go to infinity. This series actually diverges, and there's a very interesting reason why. If you find that there's a very good reason for this to be true, then go ahead, research this question. But yeah, this series actually diverges. Taking a better example, it actually comes from your partial fractions. So if you have, let's say, a partial fraction, which is like, the worst you're going to be working with is 3 factors at the bottom. So let's say the top expression equals p, and we have 3 linear factors: x minus alpha, x minus beta, x minus gamma. Now, if actually let's scale back. Let's look at 2 factors first to kind of illustrate the point I'm trying to make. If you get some form a x minus alpha minus b x minus beta, and forgot to say, but if you're taking the sum of this from, let's say, x equals 1 to n, then if you were to just look at this expression right here, if it can be written in the form a over x minus alpha minus b over x minus beta, crucially with the minus symbol over there, then what you can do is you can apply the difference method. The difference method essentially asks you, if I were to sum all of the terms of the sequence together, because clearly the sequence is getting smaller and smaller and smaller up until n, am I going to get some terms that terminate? Well, am I going to get some terms that terminate? By that I mean, do I have some terms that are like each other within the 2 sums that I have? Because obviously I can, distribute the sum between them. So really the question you're asking with the difference method is, can I cancel some numbers out if I were to write out the full expanded version of these sums, kind of ditching a big sigma notation there. And the idea of limits applies there as well, because this is a fraction, and as x becomes larger, and this is just a constant p, this does go to 0. So the limit as, I should say x goes to infinity of p x minus alpha over x minus beta. This expression right here will have an x squared term predominantly. So basically this expression right here, because this is the denominator, it blows off to some incredibly large number. So maybe with 100 million trailing zeros, let's say, then this number will be basically 0. Thus you can say, at least with a little bit of confidence, that this expression just equals 0. So yeah, we've confirmed this converges to 0. Why does that help us? That helps us because now we know that the series is converging rather than diverging. Converging means it approaches a certain value. If we apply that idea, okay, we can get something like a fraction with linear factors. If we were to split that up into partial fractions like so, over here, and crucially those 2 partial fractions are subtracting each other, then clearly, because there's going to be some like terms over here, because you start from the same value and end up at, let's say, n, then you're going to have terminating terms in the sequence. So some terms in the sequence, they cancel out, and you have to be aware of that. And that is one method in which you can evaluate sums which are kind of this form. Lastly, what you're going to be asked for is evaluating limits to infinity of these sums. And they're most likely going to come up with these sums because they are very obviously converging. It's not, well, it's never that you're going to see a geometric series in your paper, even though it is present in the spec. because it hasn't been seen up until now. With this, however, this is a pretty common question. I think the 2018 paper had one which was pretty difficult. So this sort of question pops up fairly often, and it's worthwhile kind of practicing going over this. And the topic's called telescoping series, which will be the topic of our next video. Right, I think I'll conclude the video there. Thank you.